Okay, so basically what we're doing is we're now going to go into the actual circuitry of the retina. I think that the first lecture that on this, now that we've gone through the anatomy, that are sort of like seeing what the layers of the retina are, et cetera, it's to basically approach it from a physiologic standpoint, kind of understanding how they work together, and then it makes it easier. It almost makes the layers a byproduct of all of the stuff you know about the actual cells themselves. So I'm going to start just kind of an overview of the cells of the retina, and then the subsequent lectures are going to be basically each individual cell and how it fits into the bigger picture. So so again, I always start with something familiar. I always find that starting with something that, even if the screen is literally the same thing, will make you feel more comfortable because you've seen it before, even if it's the same thing over and over again. So that's what we're looking at, the normal retina. This is the retina that we're looking at. Again, it's not pathologic, but now that's hammered home. It's the OCTs are the interpretation of light. They're not the actual pathology itself. We're looking at the standard OCT nomenclature. This is basically the one that I like to use to get all of the layers and what their names are. And so you guys can kind of always look at that. We're looking at this spot. We're going to look at this OCT again. And again, foveal depression, just rehashing the vitreous, then we identify, we went through the bands, we went through the lines. And so, we went through both of them. So now our focus is where the cells are located and to whom they talk. That's the key to this lecture, just kind of a brief, an overview. I don't know how brief it is, but it's an overview. Right. So here is kind of the thing that I want you to remember. From a general perspective, there are 7 types of cells in the retina, okay? And I'm just gonna go through them and I color code them. Sorry, RPE is a little bit kind of hard to see, but it's RPE, photoreceptors, bipolar cells, ganglion cells, horizontal cells, amacrine cells, and Mueller cells. Like, that's it. Like, those are the types, okay? There may be one wayward cell here and there, but really, if you look at it, these are the types of cells that you are going to deal with in the retina. It's not more complicated than that. It's just these. So let's come up with a framework to kind of organize them in our heads. The first framework that I like to do is I call them the main neurons, or the big 3. I don't know if you ever watched sports. If you did it back in the day, or, any time there's like a basketball team or formed, they always call them now the big 3. And it really started with like the Chicago Bulls, where they had Michael Jordan and Scottie Pippen and Dennis Rodman. So I view this as Michael Jordan, Scottie Pippen, and Dennis Rodman, if you will. Okay. So you have the photoreceptors, the bipolar cells, and the ganglion cells. This is your big 3. These are your like all-stars. They're on the court. If they don't work, you don't have a retina that works. These are your main neurons. They're the neuronal connection. This is like, if you wanted to, attack the retina, you would have to get rid of some of these guys in order for the retina to lose the game, so to speak. Okay. So that's the main neurons. But then we kind of have another kind of set of what I call support neurons. So this is like, the starting 5, right? This is the horizontal cells and the amacrine cells. They're still neurons, but I call these guys summation neurons. So they take a bunch of information from different groups of the big 3 and sometimes other cells, and kind of put it all together and sort of help out. And so you can imagine, this is the neuronal team, the starting 5. There are 5 players in a basketball team. You've got your big 3. And then of course those other 2 guys are really important in order for you to like win championships. So this is your kind of team of neurons in the retina. That's how we look at it. Your main neurons, the big 3, and then your summation neurons, as I like to call them, the horizontal cells and the amacrine cells that help these big 3 kind of work. And then of course the other 2, because we said we have 7 cells, these guys are not neurons. They're not neurons, okay? Or rather, we don't think the Mueller cells are neuron. So there's, they're glial cells, but like they're support cells. I call them like kind of like the guys on the bench, or maybe the coach, or like, something like that. The RP and the Mueller cells, these guys are kind of like, they're not maybe participating in the neuronal transfer of information. They're not taking the ball and putting it in the hoop, so to speak, but they are actually there and they're very important. Maybe the Mueller cells, like the guy who gives you the towel on the bench or whatever. And the RPE is maybe, like you said, like the coach, he's like the foundation of it, but they're not on the court, okay? They're not the ones actually going in and transmitting that electrical impulse. And this is your retinal cells, all of them. So if you framework it like this, it's kind of easy easier to remember. Just so we remember, the two that everyone forget are the amacrine cells and the Mueller cells. Those are the ones they always forget. Everything else they kind of, for whatever reason, remember, but those are the two they forget. Just putting that in your head. So these are your retinal cells. There's no like other retinal cell. And remember, there's some of them are neurons, some of them are not. Okay, so we're going to just focus on each one of these iterating through. So first we're going to focus on, I mean, I guess you could say Michael Jordan. We're going to focus on the photoreceptor because that is kind of the key to what makes the retina the retina. So if we go through the photoreceptors again under the title of, or the grouping of main neurons, it's the first step in the chain, right? There are 100, it's split up into two, you know this, rods and cones, 120 million rods and 6 million cones. This 20-to-1 ratio, just always remember that because it's very helpful. There are fewer cones than rods. This is from your book. And most everything what I take it's from your book. So or your BCSC book. So I'm trying to kind of like present it to you, but like not so that you, when you read it, you're like, oh yeah, that's correct. He's being consistent. So one of the things that we want to go through is kind of how a photoreceptor works. So the key like counterintuitive aspect of a photoreceptor is this, that in darkness, when it is dark, okay, the photoreceptor is activated. And activated also means, remember how neurons work when they're activated, depolarized. So the photoreceptor, when it is dark, is depolarized or activated. And what does that mean? Whenever a neuron is activated, it, generally speaking, at its synapse of its axon, is secreting some kind of neurotransmitter. The photoreceptor secretes glutamate. So in a dark state, the photoreceptor is activated, thus it secretes glutamate. Now, what happens when a photon comes down and hits that photoreceptor? You know, intuitively, you'd be like, oh, that's an active situation. But in reality, what is it doing? It's inhibiting the photoreceptor. Or another way of saying that from a physiologic perspective is it's hyperpolarizing. It is not depolarizing because that means active. So in this case, light, a photon of light hyperpolarizes, which stops glutamate from actually being secreted at the synapse. Does that make sense?
Yes.
Okay, so very clear. And by the way, notice what I've written here. There is nothing else that is being secreted by the photoreceptor. The photoreceptor actually, oddly enough, is pretty simple. It's kind of like, well, Michael Jordan's not simple, but like, you know, Michael Jordan gets the ball, he scores, right? Like, it's like very like simple, like there's no like, you know, that's what he does. That's what he does, okay? So, you know, in this way, it's like, it's not like, oh, well, sometimes it's like some random neurotransmitter that it's going to do. And occasionally light does this weird thing to, no. The photoreceptor literally does this. This is what it does, okay? Its complexity is in how it receives the photon, but it's not complex in terms of what its response is once it's received the photon. This is what it does, okay? So remember, light stops glutamate secretion at the synapse of the photoreceptor, okay? It stops it, okay? So here is a cartoon, I guess they call it, you know, a image from your book, literally taken from your BCSE book, and you can see the two different types. You see a cone and a rod here, and you have connections between the photoreceptor and its downstream neurons, generally speaking, the bipolar cells, but some other stuff as well. And it's just showing you up there, okay? So what I like to do is create like what's called a truth table. It's because the entire thing is a circuit, okay? And I don't know, like my approach to this is to kind of hammer home the same concepts, but from like 47 different angles. That's the idea. So I just told you in that little flowchart form. Now we're gonna tell you in a different way the same exact piece of information, and one of them will hopefully stick. So here's one thing, whenever we talk, and this makes you talk it out, which is actually, I think, better because it makes you understand. But remember this, one of the things that I really want you guys to not do is I don't want you to use the words on and off. And the reason behind it is because some of the cells have a specific on and off characteristic, like they're literally named on or off. And it's going to be confusing if you're using activation as on instead of just using the word activate. So I always say instead, always use activated or inhibited because it linguistically focuses on actions, like the action potential. It makes sense. Human beings understand that. I don't even like the idea of depolarized or hyperpolarized because they confuse people by inverting the activation.
Right.
because the word D and activate are together, but no one understands it. And so, you know, I will say, like, people will imprecisely mash words. Here's a sentence that's really bad, even though the sentence itself is still confusing, like even when it's good. But here's bad. When the light is off, the photoreceptor is on, which turns on the bipolar off cells, turns off the bipolar on cells, and thus depolarizes the ganglion off cells, while the remaining ganglion on cells are hyperpolarized. That, like, literally, I don't understand what that sentence even means.
Totally.
It's because people are mixing all of these different, you know, verbs to describe basically the same thing. This one's a little better, even though this is still kind of confusing. I like this. When it is, or instead of saying when the light is off, just say when it is dark, which is the same thing, the photoreceptor is activated, which activates the bipolar off cells, inhibits the bipolar on cells, and thus activates the ganglion off cells, while the remaining ganglion on cells are inhibited. You still have to parse that, but I think that's easier to understand. So from my perspective, that's the way you should use activate, inhibit. And then what you can do is you can replace the word activate and inhibit with whatever it is you want. Activate is also means depolarize. Activate also means on. But you don't have to actually use that word because it'll confuse you. Does this make sense?
Yes.
Okay, so that's it. I find the second easier to understand.
Yeah, that's great.
So here's our photoreceptor truth table. Now, in the left is the sort of light or dark situation, and 0 is going to be dark, okay, because a photon isn't being, you know, emitted, and 1 means there is a light, there is a photon that has been secreted. So for that is a 0, 1. So for a photoreceptor, right, in order for it to be activated and be a 1, light basically has to be at 0. Does that make sense?
Yes.
Okay. 1 just means that it's active. I'm just giving it a way to understand. Absolutely. So you would have a 1 here. And then the opposite is true. So now you're kind of just in a different way seeing there's that inverse relationship here between light and photoreceptor in terms of activation. If we think of, you know, the sun being active in terms of light being active, right, when it's emitting light, and then being inactive when it's dark. Okay, so that's kind of what we're kind of showing.
I love this. Yeah, no, this is great.
So this is helpful, I think. Okay, so that's good. Now, I like to do, so from a different angle, here we go. Where is this photoreceptor? So I'm going to show it to you, and I try to color code it. So we have dark blue as being the photoreceptor. So here's your photoreceptor, and I'm doing from end to end. The photoreceptor, you know this, its distal or outer part is in the interdigitation zone. We went through that yesterday. And then its actual, where is it synapsing? It's actually synapsing in the outer plexiform layer. So this is where the photoreceptor is, okay? And then the other thing I'll point out is that its nuclei make up the outer nuclear layer. So just to kind of iterate or re-emphasize how ginormous the photoreceptor is as it pertains to this image. Now, I know I've kind of like squished up this image so it's kind of like taller than it should be, but look how big the outer nuclear layer is, and you can see those are all photoreceptor nuclei. Okay, so literally, I always joke, it's like they get like the garden apartment. They live, the nuclei of the photoreceptor, they live in one entire layer by themselves. They get one whole nuclear layer by themselves. And that's just something to remember. So that's how a photoreceptor looks. Okay, all right, so that's photoreceptors. So now we're going to go to, I guess, Scottie Pippen here, who is the bipolar cell. Okay, bipolar cells are the next one. So bipolar cells, again, within the schema of the main neurons, they are an interneuron. What is an interneuron? They connect from one neuron to another neuron. The photoreceptor doesn't do that. The photoreceptor receives light and then goes and transmits some kind of information to another person, another neuron. In this case, it's neuron to neuron. So the bipolar cell is, by definition, an interneuron. There are 36 million bipolar cells. Now remember, we had 126 million photoreceptors, and now we have 36 million bipolar cells. So by definition, bipolar cells are getting more information on like a 1-to-4 kind of ratio than on average than the photoreceptor. So it's kind of like it's kind of like taking in more information, each bipolar cell. And you'll see this kind of theme of this like pyramidal kind of structure of information flowing more and more into one cell who has to make sense of it. So the bipolar cells are taking in basically on average 4-to-1 kind of cellular information, if this makes sense. So of course, it transmits from one neuron, photoreceptors, or Michael Jordan, I suppose, to another, the ganglion cell, which is going to be something we talk about next. And then, you know, this is what their job is effectively. There are greater than 10 total. Now, when I say that, I just mean different types of bipolar cells. There are 36 million of them, but there are greater than 10 different types. When we get to bipolar cells, we'll go through them, but that's what they are. And there are immaterial of whether, 10 different types. There's an on and there's an off form. So it's almost like you have different kind of ways of like splitting up the bipolar cells. There's going to be a type of bipolar cell, and then that type can be on or off for the most part, okay? There's always exceptions to each rule, but that's what it is. So a bipolar on cell and a bipolar off cell have different responses to what the photoreceptor is doing. A bipolar on cell is inhibited by glutamate, but a bipolar off cell is activated by glutamate. Why? And this is going to be just thinking of it, understandably so. It kind of makes sense. When it is dark, you get glutamate secretion. Why? Because the photoreceptor is active. As we said, activation of the photoreceptor occurs when it is dark. So thus secreting glutamate. Okay, well, if it secretes glutamate and then it goes and as that glutamate is going to deal with or activate one of the two bipolar cells, well, it makes kind of sense that it would be the off cell, because off in this case is actually referring to light. I mean, thank God in a way. I mean, it's a little more complicated, but at least it makes sense kind of like nomenclature wise, that when there's darkness downstream, even if I skip the photoreceptor, the bipolar off cell is active because the off cell would be doing its thing when the light is off, if you want to use that term. I hate using it like that, but if that makes sense. The reverse is true when there's light on. When there's light on, what's going to happen to glutamate? You tell me.
So glutamate gets inhibited.
Right, there is no glutamate secretion, which means that the on cell is active in that scenario. We don't have to care how it gets activated. I'm just telling you that that is what you see. So in these two scenarios, it makes sense that the bipolar off cell would be active in the first case, and the bipolar on cell would be active in the second case. Does this make sense, kind of?
Yes.
Okay, you don't have to care about what bipolar on and off means. Just know that different colonies of bipolar cells are going to be active when light is when it's light or when it's dark.
Got it.
So now we're going to do this truth table, okay? Now I'm going to let you kind of talk me through this, given our nomenclature. So if it is dark, which I show as a 0, is the photoreceptor, do I put a 1 or a 0 in this next spot?
You put the 1.
1.
Yeah.
So then what is going to happen to the bipolar on cell? Is that on cell going to be active or inactive in this state?
It's inhibited.
Inhibited. You got it. Or inhabit. Yeah, I like inhibited. I like inactive. I like them both. Okay. How about the reverse? If light is active, if we have light in a light state, what is going on with the photoreceptor in terms of its activity?
It is inactive. It's not
inactive.
Glutamate.
You got it. And remember, this is for our nomenclature, our vernacular. If we were to like be quizzed on it, you would immediately switch. You say, when I say inactive, I mean hyperpolarized.
Right.
Does that make sense?
Yep.
Right.
Yep.
So you would say that when you were standing and talking to someone who is like of a professorial type, but between you and me, we both know what we mean when we say inactive. Okay. So if this is 0, then what is happening to the bipolar on? Is he active or inhibited?
He's active.
You got it, or inactive, whatever. Good. There you go. So he's active. Okay. So that's the truth table. And you can see there's a concordance here. I'm just trying to point out, like, that's what he's concordant with. That's the kind of information at the downstream that he's kind of picking up, is that the light is in a light state. The bipolar on cell is going to be active. Let's do the same thing with the bipolar off, not to belabor the point. Light, when it's dark, we have a 0. Photoreceptor, what is that, a 1 or a 0?
It's a 1.
You got it. What's the bipolar off in this case then? Is it active or inactive?
It's active. 1.
Which means a 1. Exactly. And then when it's 1 here, photoreceptor is active or inactive when the light is when it's a light state?
It's light. It's inactive.
You got it. And then what happens to the bipolar off?
The bipolar off is off.
Is inactive.
Inactive, yes.
Right? Try to use, you got it, right? Because then otherwise you get stuck where like the bipolar off is on.
Off is on, yeah.
And then it sounds ridiculous. Right? Yeah, and I'm just saying, like, I've done this for years at this point. Like, I will say things like that too. So it's not just you, but it's helpful to just remember. So there we go. Now the bipolar off and the photoreceptor share the concordance. It's just trying to show you, like, where they share, where they're both, whoever's active, who they're following. It kind of helps to see that. Okay, so where is the bipolar cells? Well, we see here that the bipolar cell is actually connecting between the ganglion cell and the photoreceptor. So he kind of sits like this, like almost like a bridge. Outer plexiform layer is where he actually synapses with his first synapse, his dendritic, I suppose, synapse with the, or his initial synapse with the photoreceptor. And then of course in the inner plexiform layer, it's synapsing with the ganglion cell. But where's its nucleus? Well, its nucleus is in the inner nuclear layer. That's where he lives. I use the nuclei as a proxy for quote unquote where they live, if you will. So he lives in the inner nuclear living. If you ever have to guess like where a nucleus is, inner nuclear layer is a pretty good bet. Okay, so I'm just saying, I mean, it really is. Okay, so here you go, internuclear layer. Okay, now let's go to the next one. I guess this one is based on my basketball metaphor. This is ganglion cells. This is Dennis Rodman. I don't know. Yeah. So, or maybe it's Chris Bosh if you're a Miami Heat
defensively. I mean, you can't forget.
Exactly, defensively. Yeah, you got it. He's part of the big three. Okay, so ganglion cells, pretty much one of the most important neurons. So there are 0.7 to 1.5 million cells. I often just take 1 million as a perfect kind of number. So think about it this way. So if there's 1 million ganglion cells, we went from 126 million photoreceptors, 120 million rods, 6 million cones. Then we went to 36 million bipolar cells. So it's 4-to-1 dialed down. And now we get 1 million ganglion cells that are receiving all the information from the bipolar cells. So it's basically a 30-to-1 ratio. And then on top of that, the ganglion cells are taking 120 million photoreceptor pieces of information, so to speak, and it's being funneled into 1 million ganglion cells. So 1 million ganglion cells have to make, each one ganglion cell has to make sense of 120 kind of ratio cells of photoreceptors, so to speak. It's not exact, but that's on average. So you can already see how important those ganglion cells are. And then when we say something like, oh, clinically, glaucoma causes a thinning of the ganglion cell layer, which I don't know if you know that, but that's what happens. Well, guess what? That's a big deal, right? Because when you get loss of the ganglion cell layer, you're losing these cells who take into account every one ganglion cell loss is almost like average 120 photoreceptors are dying.
Yeah.
So it's a kind of one of those, it's not exact science here, but it's like you can start to see what the kind of the how important these cells are. So remember, now what does this do? This is also an interneuron. It transmits from one neuron, bipolar cells, all the way to another, the LGN cells. You remember this, right? So in the lateral geniculate nucleus, the axon of the ganglion cell is actually synapsing. So the ganglion cell axon is huge. And where does it go through? It goes through that nerve fiber layer, if you remember. That's the axon of the ganglion cell. So that's what the nerve fiber layer is making up. It's all the axons of the ganglion cells. And they're going to go right through the optic nerve, right? They're going to go effectively through, you know, the chiasm, the optic tract, and then they go into the LGN and they're going to actually synapse. That's how long it goes. Okay. So these guys are that super important. And when glaucoma takes these cells, it's really, really rough. There are 5 classes or types of ganglion cells, just letting you know, we get into it in the future, but there's also this on and off form again. So we're back to this like weird, like, okay, like you have types, but then you also get this duality, like an on and off form. One wears one hat, one wears the other. At the very least, this is really nice. Generally speaking, the bipolar on cells activate the on forms, the bipolar off cells activate the off forms. So thank God for that. So that's very helpful. So here, we're just gonna show you the schematic that I keep showing you. Here's in dark. We know what gets secreted, what neurotransmitter gets secreted in the dark.
Glutamate.
Yeah, that's literally the only one you know. So at this point, so glutamate gets secreted in the dark, which then activates the bipolar off cell, which then activates downstream the ganglion off cell. In the light, glutamate stops getting secreted, which activates the bipolar on cell, which activates the ganglion on cell. This is much more concordant. So it's almost trivial, but we still go through it because I think it's important to just do it from a different angle, and you're going to read it off for me. So remember, look at all the cells you're looking at that I've listed here. We're talking about a ganglion cell on truth table. So that's what we're doing. We're going to say, okay, in the dark, what is the number that we put for the photoreceptor?
1, because it's activated.
You got it. But then what happens to the bipolar on cell in that state?
It's deactivated.
It's inactivated. And so it's a 0, which means what's happening to the ganglion on cell?
It is also inactive.
You got it. 100%. So now what about when we're in a light state? What happens to the photoreceptor?
It is inhibited. So it's hyperpolarized. It's deactivated.
You got it. Then what happens to the bipolar on cell?
It's activated.
You got it. And then what happens to the ganglion on cell?
It is also activated.
You got it. So remember, this concords with this, which concords with this. Makes sense because, again, intuitively humans understand, you know, that if the light is quote unquote there, it's the light switch is quote unquote on. I hate using that, but it kind of works here. Light is on, therefore bipolar on is active, therefore ganglion cell on is active. Let's just rehash the point here so you don't forget. And this is also just to keep reminding you about the photoreceptor, so that's always helpful. So we're going to do the ganglion cell off here. So if in a dark state, what's the photoreceptor? Active or inactive? Active. What about the bipolar off cell then in this case?
Inactive.
So let's think.
So bipolar off cell, photoreceptor.
Right? So if the photoreceptor is active, the bipolar off cell is active, right? Because remember, the bipolar off cell is concordant with the state of the light.
Yes.
Makes sense? Mm-hmm. So then the ganglion off cell is actually active. Does this make sense?
Yeah, absolutely.
Right? This is confusing. That's why they on and off. Look at, that's why I do these truth tables, because I'm like, wait. So it's concordant with whether it's off. The zero there is like 1 for darkness. Okay. The zero there and there is like 1 for off, if you will. Right. But it's like, I write it like that because a photon is going to be confusing. So if the light is active in this case, then what is the photoreceptor? It
is inactive.
You got it. Which means what happens to the bipolar off?
Which is also inactive.
Correct, which means what happens to the ganglion cell off cell?
Which is inactive as well.
Correct. So you have the concordance. So the off cells basically follow the polarization, so to speak, of the photoreceptor because it is the antithesis of the light, which is counterintuitive, but it is. And then the on cells follow the light. So the off cells follow the photoreceptor, the on cells follow the light, so to speak. You get what I'm saying?
Yep.
That's right. Okay, so we're going to do it now from a different angle, just because this is confusing. So I do it just from this way. Okay, so we've got now from 2 different sides. Okay, so we've got our light and our one side is darkness, one side is light. Here's our photoreceptor. Okay, and then I'm going to show you these 2. And these are your choices in this tree. And then here's your choices in this tree. So I'm going to say, let's do a dark state. Okay. So we're blocking out the sun. So we're going to go on this left side over here. Okay. So we're blocking out this side. So what happens? Which is the photoreceptor active or inactive in this state? In the darkness?
Activated.
Good. Active. Which means which one? Bipolar on or bipolar off in this state is going to be active?
The one that is active is the bipolar on cell.
When it's dark?
When the light is off. Bipolar off cell, sorry.
You got it, right? So that one, and then if the bipolar off cell is active, then what is active? Ganglion cell on or off?
Yeah, the ganglion cell off.
Yeah, so this is the way this line goes, okay? It goes like this. So let's now flip our minds and go over here. Let's see, when the light is on, so to speak, is the photoreceptor active or inactive?
The photoreceptor is inactive.
You got it. So we gray it out. So when he's inactive, who is active?
On cell.
Correct.
Active.
And then who is active in this case then?
The ganglion cell on cell as well.
You got it. So this is the way this looks. Okay.
Oh, that's great. It's a good way of.
So it gives you a different way of looking at it. Okay. So I like to just kind of each just go in different directions. So this will be helpful. Okay. So let's figure out where that ganglion cell is. So the ganglion cell, you know, is here. This is how he is, except his axon continues out off the page here. Inner plexiform layer it makes up is where it synapses with the bipolar cell in the canonical sort of pathway. And then the nerve fiber layer is when it goes and sends its axons out. But it also, like the photoreceptor, gets the ganglion cell layer for its own nuclei. So you have these 2 cells, the photoreceptor and the ganglion cell layer, they get like the garden apartment and the penthouse. And then everyone else has to live in like with the masses, so to speak, in the internuclear layer. So the internuclear layer is actually where, again, if you're going to guess, that's where you throw a nucleus in, but the other 2 get their own layers. Okay, so now we're done with the big 3. We're going to go to, I don't know, Steve Kerr and whoever is playing else, right? Luke Longley or whatever. So the point is, now we're going to talk about the summation neurons, the other guys over here. What do they do? Okay. So let's first start with the horizontal cells. So the horizontal cells, what are they? And I say summation neuron. They integrate input from multiple photoreceptors. So now we're already thinking multiple photoreceptors. We already know where they should be. They should be at the outer edges of the retina somewhere, okay? They're not gonna be up by the ganglion cells if they gotta interact with photoreceptors. So you already know this in your head. You keep that in mind. it takes into account sums of multiple different neurons. It's activated by glutamate. Now you're like, wait a minute, let me just remember, when do we have activation of glutamate, or when do we have glutamate being secreted? Well, we have glutamate being secreted when it's dark, exactly. And who's secreting it? The photoreceptors. Okay, this is all making sense in our head. We say, okay, so I just straight up say, okay, activated by photoreceptors in the dark. But here's the weird thing. They inhibit surrounding photoreceptors. So when they're active, they inhibit surrounding photoreceptors. Super odd. This is called negative feedback for surrounding photoreceptors. So we're just going to first go through this horizontal schema, and we're going to say to ourselves, okay, we're going to go through it in the 3 different ways that I talked about. So in darkness, we have the central. Now we're no longer just saying the photoreceptor. When we talk about photoreceptors, now we're going to say the central photoreceptor. That guy is activated, which means he's secreting glutamate, which means that the nearby, whatever that means in this case, horizontal cell is activated, because again, he's activated by glutamate, thus he's activated by photoreceptors in the dark. But then what does he do? He goes and inhibits the surrounding photoreceptors. That's what he does. So he basically doesn't even care about anyone else. He's just connecting from one photoreceptor to another photoreceptor. In this case, we've denoted a central photoreceptor and a surrounding photoreceptor. And he just basically is activated by one guy and inhibits the guys around him. In the light, the central photoreceptor is inhibited. The horizontal cell thus is inhibited because no glutamate's being secreted. And then of course the surrounding photoreceptors are now activated. Okay, so it's this inversion. So it's like, it's kind of, you have to wrap your mind around what's going on here. So I'm going to just say, okay, let's just do this and like kind of, let's figure this out. What's going on? Light hits a central photoreceptor. The central photoreceptor is now inhibited. Remember, when light hits the photoreceptor, it inhibits or inactivates that photoreceptor. So he's no longer secreting glutamate. Thus the horizontal cell is inhibited. Thus the surrounding photoreceptors are activated. But like, why is this happening? Is the horizontal cell just doing stuff just to be what it's doing? What's going on here? What is the reason for this? Well, this is the point. It's reducing the surrounding noise and thus increasing the signal of the central photoreceptor. So a horizontal cell is a classic example of what's called lateral inhibition. How do we kind of understand this? Think about it like you're having a party and you're the central photoreceptor. This guy is your buddy that moves, he listens to your music and then he moves horizontally and tells your next door neighbors to do the opposite of what you're doing. So let's say you're playing music. He says, turn down your music so my music doesn't have to be louder. It's going to be louder by definition because you've relatively reduced your music. Does that make sense?
Yeah, absolutely.
So that's what the horizontal cells do. They potentiate whatever the signal is of that central photoreceptor is. So that's what it's doing, okay? And so thus the horizontal cell is super important. And where does he live? He lives wherever the photoreceptors live. So let's do from another angle now, okay? We're gonna now go, again, here's a truth table. We're going to now, instead of just saying photoreceptor, we're going to say central photoreceptor. And we just went through this. And then, of course, the horizontal cells over here. And then now it's a surrounding photoreceptor that we're going to, be at the edge of this truth table. So again, as we start, here's 0. So in the darkness, photoreceptor central, is that central photoreceptor active or inactive?
It's active.
You got it. And then what is the horizontal cell that's connected to him? What is he, active or inactive?
He is active as well.
You got it. And then what does he make the surrounding photoreceptor? What does he do to them?
He inactivates.
Yeah, or inhibits, whatever you want to say. So 0, perfect. You got it. How about we flip it? Now we have a light we have a light state. Now what is the central photoreceptor? Is he active or inactive?
Inactive.
You got it. And then what does that do to the horizontal cell?
Also inactive.
You got it. And then what is that going to then do for the surrounding guys?
Activates them, which I guess makes them more sensitive to any input. If you're not getting input from one, you upgrade.
Right. So exactly. So we know horizontal cell basically leaves no doubt. If you're looking at the colony from above, the central photoreceptor is whatever it is, because the surrounding ones are kind of doing the opposite by definition. So that guy, his signal is what it is because it's even more potentiated. Makes sense?
Yep.
So you can see these guys are concordant, and then These guys actually are interestingly concordant, weirdly enough, but you don't have to care about that. Like light and the surrounding, it's kind of weird. So I don't like to think that way. So let's introduce here the surrounding photoreceptors. So those are the central photoreceptors. This is again, looking at it from a different way and then putting an horizontal cell here. Okay, so now we have a horizontal cell. So now we're going to block off the sun, kind of the light phase, and we're going to look just at the dark phase. So now you're going to tell me, first, let's go just through the central photoreceptor. If it is a dark state, is the central photoreceptor active or inactive?
It is active.
Okay, so that's what we're going with. So it's active. Okay, now if it's active, then what about which one is the horizontal cell active or inactive?
It is active as well.
Good. Now tell me what happens to the bipolar. Is the bipolar on or off cell active? Which one is active?
The bipolar off is active.
You got it. And then what? Okay, so you got it. And then what happens here to the surrounding photoreceptors?
So on the layer above, they are inactivated.
Good. And then which one, ganglion cell on or off? Which one's active or inactive?
Ganglion cell off.
You got it. So it looks like that.
Interesting.
Makes sense? Now, here's the thing. Once you've written this down, like once you get this, then you know whatever's I've brightened here, you know, what does that mean? Actually, it doesn't just mean active. It means depolarized. It's just another word. So now if you learn like a test, you're like, oh, I made this line. Okay, depolarized, everything else is hyperpolarized.
Yeah, yeah.
Right, in this thing. And just so you know, right, this is just another side of the truth table. So this is not actually both of these. It's like basically this sliding scale right over here, right? And so, you know, what I'm saying in effect is you can now just rehash your words so that the OCAPs or the boards guys or the boards test understand what you mean in terms of the actual physiology and start using the nomenclature that real biology uses. But in your head, active, inactive, active, inhibit, it's so much easier. So now let's go to the light phase. So we're going to turn off this guy, or I shouldn't say that. We're going to just eliminate this guy. And we're going to go over to the right here. In a light state, what happens to the central photoreceptor?
There's inactive.
You got it. So it's inactive. Which one, bipolar on or bipolar off? Which one is active in a light state?
The bipolar on.
You got it. And then ganglion cell on or off? Which one is active in a light state?
The ganglion cell on.
Okay. And then we got this, and then the ganglion cell on. And then is the horizontal cell active or inactive when the central photoreceptor is inactive?
It is inactive.
Good. And then the surrounding photoreceptors, are those active or inactive now?
They're now active.
Right. So you got this schema. Okay. Makes sense? Mm-hmm. Okay. And it like, by the way, like you may forget it, but then you can walk yourself through it slowly. And then you're going to say these questions that I get asked on the OCAPs, they're going to be layups once you understand this stuff. I mean, I think they ask you some of these questions.
Yeah, they do.
Totally confusing if you're just like, oh, I don't know. But now you're like, hey, I think I get it. And I think I can walk my way through it. So let's figure out where the horizontal cell is. Well, we already know that he's going to be like kind of almost like grabbing on with two hands or multiple feet. But all of his hands and feet are touching photoreceptors. So by definition, he's going to be kind of in this zone where he is kind of sliding or straddling the outer plexiform layer, because that's where the post-synapse is, where glutamate's being secreted by the photoreceptor. But then, of course, you know, when in doubt, where's his house going to be built? Where's his nuclei going to be? In the internuclear layer. Again, that's where everyone lives. Okay.
Yep.
All right, so let's now do amacrine cells. Okay, now amacrine cells are a little bit more kind of nebulous. You'll find that as we percolate upward, amacrine cells don't have as easy of a defined term. They're a support cell, again, they're an interneuron. They integrate sums from like bipolar cells and ganglion cells. That's usually, so they're kind of like the inverse, but they also have bipolar cells connected to them. So it's a little interesting. There are like 33 different types. By the time I give you this lecture, there's going to be like another 10. Like it's just constantly being added to. They are important for all these very, very qualitative things like scotopic vision, directional motion, and light adaptation. I don't have any truth tables for them because they're so unique. And when we get to their section, you'll understand why. But where's the amacrine cell? They're kind of like the mirror image, if you will, in a way, of the horizontal cell, which straddles the outer plexiform layer. This guy straddles the inner plexiform layer. But then where is his nuclei? Well, again, it's in the internuclear layer. It's like, there you go. So he is just where he is, sitting right there. Okay. Now let's go to the support cells. You've got your RPE and your Mueller cells. So we're going to, and now we've completed all of the retinal cells. I mean, you have 7. We're basically gone through all 7. So let's go first through the Mueller cells, which you already know, we talked about it. They're support cells. They're not neurons. I'm going to just say it again. They're not neurons, okay? They're classically, their nuclei are, where would you guess it? The internuclear layer. But you already know, right? And they're a glial cell, so they're not neurons. They help regulate the extracellular environment. So again, they're kind of like, I like to think of the Mueller cell. I don't know if this is like insulting or totally not, but they're like the water boy and they give Gatorade. That's what I always say, because they regulate K levels. So they hand Gatorade to the team, you know, like with the electrolytes and stuff. They regulate K levels, they insulate, they give the guys a towel, you know what I mean? Like to wipe them off and stuff, right? Insulation, right? The mechanical stability, they give them a chair to sit down on, right? They're that guy, right? And so you know where they sit. Here's your Mueller cell sitting right in the middle there. You know that where does he start? His head actually starts at the external limiting membrane, where he has the tight junctions between him and the photoreceptors. And then, of course, his foot plates are at the inner limiting membrane, which we know. But then where's his nuclei? His nuclei, I didn't write it here, internuclear layer. Classically, that's what they say. Where else would you have guessed, right? Again, they live in the slums of the retina, if you want to call it that. Maybe it's not the slums, but it's a very important part of the retina. But they live in that area where everyone has to live, with the masses. And then, of course, you got your RPE cell. And your RPE cell, you know where this is. What is he there for? He is not a neuron again. Again, that's why they're in the green, right? The green cells, I guess, are not neurons. They're not neurons. They do this. This is literally copied from your book. They do all sorts of stuff. One of the things I like to just point out, some of the key things that I've seen before that have been tested maybe, is phagocytosis, cone and rod outer segments. They form, you already know this, the second blood ocular barrier or the blood retinal barrier, the outer blood retinal barrier, the tight junctions between the RPE, as we said. What's the inner blood retinal barrier? Do you remember?
The inner is the endothelial, the endothelium around like the retinal vasculature.
You got it. That's it. You got it. So now you know them both. And then, of course, it regenerates and recycles visual pigment, which it does both with the phagocytosis of the rod and cone outer segments. And this regeneration happens with that interdigitation zone with the apical processes kind of going around like fimbriae around the outer segments. So where is he? He's down here. I mean, like easy. You know that. Okay. RPE Bruch's complex. Okay. That's what we call him there, but that's where he lives. Okay, so we're just going to stack them. Here's your photoreceptor. Here's your bipolar cell. There's a horizontal cell kind of supporting the photoreceptors. There's your ganglion cell with its axons going into the nerve fiber layer. There's your amacrine cell. You've got your Mueller cell, and then you've got your RPE. There's your 7 cells of the retina. Okay, There you go. You got them all. Okay. And then I put an RPE down there just to show you that that's like the structure. And then maybe I should have drawn a Mueller cell over there, but like that's your structure. It's like straight up, the entire visual system really works really well from down outer to inner. Okay, and we're labeling them photoreceptor, bipolar cell, horizontal cell, ganglion cell, amacrine cell, Mueller cell, and RPE. Okay, all right, so here's a rapid review. Let's see how we do, okay? You know how I always do. It's no stress, okay? We're just gonna have some questions and you'll be kind of, I think, surprised at maybe some of what you know already, okay? So I'm just gonna label a cell and you're gonna tell me what that cell is, where it starts, where it ends, and what start and end means doesn't really matter, just kind of what those layers are, and then where its nucleus is. So what is this cell?
This is the Mueller cell.
Yep, and then where does it start or end? Give me the 2 edges here.
Yeah, so starts in the ILM.
Yep.
Ends in the ELM.
Yep.
And I believe we have the internuclear layer is where its nuclei are.
Yep, you got it. And then the nuclei are there. That's the Mueller cell. Okay, what about this guy?
That is a bipolar cell.
Good. And where does it start, end, and where is its nucleus?
Nucleus is in the internuclear layer.
Good.
Starts, well, just looking at that, looks like it starts in the outer plexiform layer.
And where does it end?
And kind of inner plexiform, or
you got it. The inner plexiform, right? Because what's above the what's inner to the inner plexiform, the ganglion cell layer, and you already know that's the penthouse. Yeah. That's where the ganglion cells live. right? You don't get to be in their bipolar cell, right? You're down in the internuclear layer. So you got it, and it's in the internuclear layer. So it is totally legal to say the way it looks, I can see it there, because you're using the OCT to figure it out, right? But doesn't it make sense? Where is the synapse between the photoreceptor and the bipolar cell? It's going to be in the outer plexiform layer, because that's where the photoreceptor is. Where is the synapse between the ganglion cell and the bipolar cell going to be? What's going to be in the one that's in between the ganglion cell layer and the internuclear layer? That's the inner plexiform. So you got it. So this is the bipolar cell. I don't know why I've capitalized P there, but okay. And then what is this guy?
This is the amacrine cell.
Think about where you're looking right now.
So we're in the.
So tell me where the bottom of that rectangle is.
So it's all the way just before, it's like the interdigitation.
Yeah, so who's involved in the interdigitation zone? Give me the two cells.
So interdigitation is, it's photoreceptors.
Yeah, so it's interdigitation is photoreceptors and what?
And
so describe the interdigitation zone. Like, just describe to me what happens in that zone.
Oh, the RPE is.
Got it. So it's RPE, apical processes, fimbriae, and then you said from above it's the photoreceptor. So what is this cell? It's either RPE or photoreceptor, right? Because that's where this foot is. So which one is it?
It's photoreceptor.
You got it. So it's the photoreceptor. You got it. So the photoreceptor's outer segment starts, or it's one side is in the interdigitation. So that's where it ends. And then where does it stretch up to?
Then it goes out to the outer plexiform layer.
You got it. The outer plexiform layer. That's exactly where it ends. That's where it secretes glutamate. And then where is its nuclei? It gets the garden level apartment. It doesn't have to, it is a huge garden level apartment. Where is that nuclei?
At the outer nuclear layer.
You got it. Perfect. Interdigitation zone, outer plexiform layer, outer nuclear layer, photoreceptor, right? Makes sense?
Yeah.
Yeah. So then what is that guy? This one kind of is easy, I guess.
Yeah, RPE.
You got it. He's RPE, Rux complex. That's just complex, RPE. Yeah, I just said RPE. Okay. Now this one, who is he? You said you thought the other guy
I thought the amacrine layer was that for some reason. Yeah.
Right, but now you know. But it's not like it's this is confusing, but like now it's like less confusing, right? Like you look at this and you're like, wait, yeah, the photoreceptor is like way down there, and the amacrine cell is like way up here, right? Because where's the amacrine cell trying to talk? He's trying to talk to the ganglion cells. And they only occur way up in the penthouse. They're not going to be down in the garden zone, right? So he's never going to like be down there. So tell me, where is this guy basically, where's his nuclei, if you had to tell me?
The internuclear.
Got it. And then where is he synapsing? The way I've drawn it, it should give you a clue.
Also between the internuclear layer and the inner plexiform layer.
So it's the inner plexiform layer. That's where he synapses. So remember, all the synapses are happening in the plexiform layers, and all of the nuclei, that's where they live, are in the nuclear layers or the cellular layers. We're still going back to that old school, you know what I mean? Like what we talked about when we first started. White is axonal and all that, those shenanigans.
Yep.
And then black is going to still be your nuclei. So in this case, you're like, well, if he has a synapse and I only see him straddling one black and one white, well, then the one white has to be, or the one light, that has to be where his axonal connections are, and then the dark has to be where his nuclei are. And so you got it exactly, inner plexiform layer and inner nuclear layer. That's literally where he lives, in that zone, and that's the amacrine cell. Okay, how about this guy?
So that is the ganglion cell.
You got it. So where is his first dendritic connection? Where's, like, you know, he's an interneuron, so he's got receipts, he's got axons sort of in both edges, both behind and, you know, both sides of him. Where's the, where does these two things? So where does his bottom?
All the way up at the retinal nerve fiber layer.
Retinal nerve fiber layer is the one. And then what about on the other side?
And then on the other end, he's at the internal plexiform layer.
You got it, inner plexiform layer. It's exactly right. And then where are his nuclei?
Looks like it's in, I mean, it's in the ganglion cell layer. Yeah. Why they call it that. Yeah.
I mean, it tells you, right? Ganglion cell layer. Yep. You got it. Yeah. That's what he looks like. And there's your ganglion cell. And then who is this guy?
And this is our horizontal cell.
And where are his nuclei?
In the internuclear layer.
And where does he synapse?
At the outer plexiform layer.
You got it. Perfect, right? Because he's only got two and he's synapsing only basically with photoreceptors, right?
Yep.
Makes sense?
Yep.
Okay, you got it. So what am I doing? Oh, now, so I'm going to point to a layer and you're going to tell me which cells are in this layer, which cells are involved in this layer.
Oh, I like it.
Okay, so tell me the layer and then tell me which cells are involved. So this layer.
So this is the ganglion cell layer.
Correct. And what is in this layer?
I would venture that the ganglion cell is there.
Yeah, and the ganglion cell what?
Oh, go ahead.
What's that?
I was going to say, yes, the ganglion cell and the Mueller cell passes through there because it passes through.
You're right. So let me put it to you this way. You're absolutely right. The Mueller cell is going to pass right through. That's actually, no one's actually ever said that. So I give you credit. Yes, the ganglion, the Mueller cell's like foot goes through it. It's shin, I suppose, goes through it. But let me just say, is it the axon of the ganglion cell or the nuclei of the ganglion cell?
This is the nuclei of the ganglion.
You got it, right? Because it's considered a dark layer. Makes sense? So ganglion cell layer is the ganglion cell nuclei. Makes sense. Okay. Now let's point to that. First of all, tell me what layer it is. And if you get confused, go back to whether dark or light. What is it?
Yeah, outer nuclear layer.
Outer nuclear layer. Now tell me what is in the outer nuclear layer.
So we have a few things there. So just the photoreceptors are there.
Right, the photoreceptors. And so what of the photoreceptor? What part of the photoreceptor?
It's there. They get it's the penthouse real estate you refer to. So their nucleus is
You got it. Nuclei, and it's also called the outer nuclear layer, right? So it makes sense, right? Yeah, that's it. Photoreceptor nuclei. So if the outer, just as an example, think about it this way. Now you understand why, like it's like kind of like if you leave chronic fluid sitting in the outer nuclear layer, which is where it connects, it's kind of toxic because what are you damaging? The photoreceptor nuclei, right? So chronic fluid sucks when it's sitting in the outer nuclear layer because it's like slamming the photoreceptor nuclei.
Less so than like CME elsewhere in.
Well, when you say less so, the question is it? I mean, when you have chronic fluid, I guess I should rephrase it. If I have chronic fluid, it tends to collect in the outer nuclear layer. And then if I end up having damage in that layer, it's going to be the photoreceptor nuclei. So it should potentiate in your head like, yeah, that really doesn't bode well because then we're damaging actual photoreceptors. So I can see where the damage would lie. Let's just put it that way. You're not wrong. Like if you have chronic fluid anywhere in the retina, you don't like it. So it's not like it's great to have it elsewhere, but it's better, it's understandable what's being damaged. Okay, let's point to that guy. What is that guy?
So it's the inner nuclear layer.
Beautiful. Now tell me which cells have their nuclei there?
The bipolar cells have it there.
What else?
Do the horizontal cells as well?
Correct. Remember we said it's the slums, right? And those guys got to live somewhere. So the horizontal cells do. Who else?
So the bipolar.
You said bipolar. So one
bipolar. And then the amacrine cells.
Amacrine cells, and then there's one more that everyone forgets.
Which would
he's not a neuron.
Oh, well, then there's only two things. So it's the Mueller cells.
You got it. The Mueller cells. So there you go. Those are the four. Okay. So you have four nuclei that sit in there and are living there doing their business, but then they're also like doing whatever they need to do in the plexiform layers. That's where the work is done, right? Okay. So what about that? What is that called?
Retinal nerve fiber layer.
Yep. And then what is going through that?
So the Mueller cells.
Well, you're right. You're not wrong. The Mueller, you're like, again, I am very.
I'm going from outside in, but it's the ganglion cell, most important, that starts there and then synapses at the inner plexiform layer.
Right. So the ganglion cell, what part of the ganglion cell is actually in there? It's their axon, remember? And that's the axon that's going where? To the LGN.
Yes.
Makes sense? It goes off the page. But you're not wrong that their dendrite, the pre-nuclear, so to speak, axon is in the inner plexiform layer, and that's what's synapsing with the bipolar cells is in the canonical pathway. Does that make sense?
Yes, yes,
So
yes.
this is ganglion cell axon 2 LGN. Okay. Okay, so what is that layer? First define it for me.
It's the inner, oh, sorry, this is the,
you were right. Inner
yeah,
what?
yeah, inner plexiform layer.
Inner plexiform layer. You were right. Remember, when in doubt, right, we draw a line, right? In this case, we draw a line through the fovea, right, and we know it's inner to that. So there we go. Now we know it's inner. Okay, so inner plexiform layer. You got it. Now, hard to do, but tell me, just give me, I'm going to tell you, make it a hint. Okay, there are 3 cells that synapse with each other, so to speak, there. They all are there synapsing. Which 3 cells synapse there? Give me.
Well, your schematic was really helpful. So it's like the amacrine layers synapse there. I think the bipolar cells,
and then who does the
and then the horizontal cells.
No. Where does the horizontal cell synapse? Somewhere else, right? Because the horizontal cell only deals with photoreceptors. So I always say, you got the amacrine cell, which is actually the hardest one. Think of the canonical pathway. Always think of the canonical pathway, the big 3. That's where we started with. It's photoreceptor to bipolar cell to ganglion cell, right? That's what it is. Where is that connection happening? Well, the photoreceptor is going to connect to the bipolar cells in the outer plexiform layer, because that's where the photoreceptor is. The bipolar cell is then going to like hand that off, that information, all the way up into where? The inner plexiform layer. And who is he handing it off to?
To the photoreceptor.
The other way. So going from photoreceptor to bipolar cell, and then bipolar cell
to the ganglion cells.
You got it. So the ganglion cell's up there, right? So you got this.
Oh, wow. Okay.
Right? Makes sense. So interplexiform, and its bipolar cells are synapsing with the ganglion cell. Just forget that I say this. And the amacrine cells are synapsing with the ganglion cells. And then the ganglion cells are transmitting all of that to the LGN. Make sense?
Oh, interesting. Yeah.
Makes sense. So there you go. So now let's do this one. It's the white layer. What is that layer?
So the white layer is the inner plexiform layer.
Say it again.
Outer plexiform layer, excuse me.
Outer plexiform layer. Outer, right? Because we draw a line. And
yep,
we know
south of that. Yep.
So which ones do this? Sorry, I already showed you, but what are the 3 cells? It's funny because there are 3 cells for the IPL and 3 cells for the OPL here. What are the 3 cells? Think about it from like structurally. What is the canonical pathway? It's photoreceptor to bipolar to ganglion cell. Which of those 2 are in this layer?
Photoreceptor and bipolar.
You got it. Perfect. And then what is the support cell that's here? Is it horizontal or amacrine?
It is horizontal.
You got it. So those are the 3. So it's like you got a canonical pathway, you know, a dyad, because that's where they're handing it off. And then you've got a support cell. That's how you can think about it to help them do that. Make sense?
Yeah.
Okay. So you got it. So it's bipolar, and it's horizontal cells, and photoreceptors are synapsing with bipolar cells. Okay. And then what is that again? Just so we don't ever forget.
Yes, it has to be dark when you're, yeah.
Okay. So now we're going to do it one more way. We're going to just talk it through. If I ask you horizontal cells, where are the horizontal cell nuclei? Think about it in your head.
They are in the inner nuclear layer.
When in doubt, you guess inner nuclear layer.
Yeah.
Where do they synapse?
Outer plexiform layer.
Got it. And with which cells? What did I tell you? With which cells is a horizontal cell? What did we go through? Who are they connected
the outer, the
got it. The photoreceptors.
The photoreceptors. Okay. Yeah.
And then bipolar cells as well. Okay, good. Photoreceptors. Okay. Where are their nuclei?
The outer nuclear layer.
Got it. Where do they synapse? So who do they?
Bipolar cells.
Yeah. So they synapse with a bipolar cell, but where?
In the outer plexiform layer.
You got it. So if ever you use the word synapse, it's a plexiform layer. Number 1.
Okay. All right.
You're not gonna like synapses don't occur in the nuclear layer. So you got it.
That makes sense. Yep.
And then you say, well, is it outer or inner? And I already told you the first the canonical pathway is photoreceptor to bipolar, and then bipolar to ganglion cell. So already you know it goes inner to outer, so outer to inner, sorry. So you go photoreceptor to bipolar cell, and that's going to be outer, and then bipolar to ganglion cell, that's going to be inner.
Oh, interesting. Yeah.
Marches its way up, and then you say, well, you get 1 supporting cell per plexiform layer, And that the first one, the one that's outer, is your horizontal cell, and the second one is your amacrine cell. Make sense?
Okay, got it. Yeah.
Okay, so in this case, where are they synapsing? Just tell me. Photoreceptors?
At the outer plexiform layer with the
outer plexiform layer.
Bipolar cells, yeah.
And with which cells? Bipolar cells, and also we said
the bipolar cells, yeah.
And then horizontal cells. So those are the two. There's no more. It's not like tomorrow there's going to be another one, right? So I always say, like, you learn this once, and then you learn it again, and then it's like history in a way, right? Like you just, oh yeah, the photoreceptors, that's what they synapse with. It doesn't change tomorrow. So it's nice once you learn it. Okay, amacrine cells. Where are their nuclei? When in doubt,
internuclear layer.
Right? Because there's only two other cells that one gets its own, like there's three nuclear layers. One is the ganglion cell layer, which is already said, and the other is the outer nuclear layer, which you just told me
which only gets the photoreceptor. So the rest are internuclear layer.
So that, by process of elimination. So you just told me internuclear layer. Who do they synapse with? They're the supporting cells, or the summation cells, I should say, but where are they? They're going horizontal cell and amacrine. They divide up. They say, I'll take this duo and you take the other duo. Where is the amacrine cell synapsing them?
Where it synapses the inner plexiform layer, because it's the inner. Yeah.
And then with which cells? Who are synapsing in the inner plexiform layer?
In the ganglion cells.
The ganglion, and who is the ganglion cell synapsing with in the inner plexiform layer, like the canonical pathway?
Bipolar cells.
Got it. So it's basically ganglion and bipolar cells, and it's just helping out. Okay. Ganglion cells. Okay. Where are their nuclei?
In the ganglion cell layer.
Got it. Where do they synapse? So where is the first synapse, the retinal synapse? Where are they synapsing?
In the inner plexiform layer.
Got it. And who are they doing that with? And
with
again,
the cells that we just talked about. Yeah.
You got it. It doesn't change, right? Now that you do it in multiple different angles. And as I say, also just remember the other synapse that the ganglion cell's involved with is, of course, the lateral geniculate nucleus, right? It goes all the way through. That's the other side, because it too is an interneuron. It's taking from the bipolar cell and, of course, the amacrine cell for help. And then it goes and sends that impulse all the way to the lateral geniculate nucleus, where it then synapses. And we get into that at a later date. And then with which cells? You just told me bipolar and amacrine, and then it goes and sends it to the lateral geniculate. Bipolar cells, okay, where are their nuclei?
So internuclear layer.
Internuclear layer, you got it. And where do they synapse? Now, these guys are they're the relay man. So they're in the middle. So where are their synapses? Give me the two layers.
The inner and outer plexiform layers.
You got it. Perfect. Yeah. It goes from outer to inner, right? Because it's taking from the
photoreceptors back up. Yeah.
Got it. And then with which cells? Here we go. This is oh God, so annoying. But tell me the canonical pathway. Who does it receive input from?
So it goes photoreceptors to bipolar to ganglion. So it would synapse in the inner plexiform layer with the ganglion cells.
You got it. An outer plexiform layer with the photoreceptors. And then just letting you know, of course, horizontal cells and amacrine cells, I'm sure, are involved there, but you got it exactly. So it's like, basically that's how it does it. Mueller cells, okay? Where are their nuclei?
Internuclear layer.
You got it. And who do they synapse with?
They synapse with I guess, out in the external limiting membrane.
Can we just do that? Remember, I said it many times, and no one ever gets this. I always say, let's see if anyone gets this. It is not a neuron.
It's not a neuron. They don't synapse. Yes, lovely.
Right, and that's what I say. They're green. I don't know. They don't have. They're the water boy, or the guy who puts out the chair and gives you the Gatorade and the towel, right?
Support.
And with cells, there are no cells. It doesn't synapse. It just kind of supports, right? Yeah. That's it, man. So
that's awesome.
Yeah, so this is good. Now, mind you, this is like the big guy. Like, there's a lot going on here, but now we're going to go through each individual one, and it becomes a lot easier to understand. But now that you get this framework, I think it's helpful. Okay.
It's wonderful. This is so helpful. This is a different way of going through it. I appreciate it.
Yeah, no problem. So I just wanted to clarify. Do you just want to email me when you're free next?
Yeah, that sounds good.
Okay, that way I know, because I'm not sure, I don't remember, and you let me know, because I know you might be on call or not on call, so you just let me know. You just send me an email, okay?
Will do.
All right, get some rest, okay?
Sounds good. Thanks so much. Take care.